Hi, I'm Ben Yeh, here with Qi Zhang, presenting our ECE3400 Project 2. The goal of this project is to understand how amplifier gain is related to device parameters for fundamental MOSFET circuits. Let's begin with a common source amplifier. It takes in a voltage Vin and amplifies it at Vout. To solve for the possible gain, we can perform KCL of the output node. If I bias is the current supplied by the source, then we have this expression assuming subthreshold operation. After manipulating it into a function of Vout versus Vin, we see that a change in Vin brings about a change in Vout equal to negative kappa over sigma. If we are at above threshold, we do the same thing but using the appropriate expression for the current through the NFET. Implicitly differentiating gives us this result. What we have done here is remove the current source and put in its place a PFET biased to supply approximately the same amount of current. We can solve for the gain as we had done before by equating the currents to the FETs, but let's proceed by working out the small signal analysis. The equivalent small signal model is shown. KCL at the top node leads to this expression for the gain. Substituting these equations for GM and R output gives us an expression like before, but unlike the case with the ideal current source, we note the effect of the PFET here. If we wanted a very large gain, then it would be prudent to make sigma as small as possible, and we'll see some ways to do that later. From a provided set of measured values of output voltage versus input, we can see that the gain as a slope of the sharp transition. This measured value set is very easily produced in the simulation, and some values for the simulation are provided next. If we can assume that the sigmas for the FETs are approximately equal, then we have these parameters for simulation. Next, we look at a differential pair amplifier, which has the configuration as shown. I1 and I2 flows through the left and right upper transistor, respectively, and combine to form I bias at the bottom transistor. So if the bottom transistor is working in subthreshold, then it must be the case that the other are as well. The goal now will be to derive the currents through each leg as a function of the difference between the applied voltages V1 and V2 as shown. Dividing either I1 or I2 by I bias produces the box expression. From this we can see that the currents are mirrored opposites of each other, and as the difference of V1 and V2 decreases, the currents through one will increase and the current through the other will decrease. Further suppose that V1 is much less than V2, then we can further get these simplifying expressions. We were provided another set of measured data to see how well it conforms to these expressions. The light blue and dark blue curves represent the currents through the left and right transistor and are each fitted with the functions to the left. And as you can see, fits quite well. We can get a value for K over UT by noting that near where the differential input is 0, the curves are linear, so we can fit a linear line to it. And because I1 and I2 converge to the same node, their sum is a constant, shown by the green curve. This is also I bias. The red curve is interesting. It is the difference between I1 and I2, and we try to fit it using a hyperbolic tangent, but we can't actually get it using the current configuration. We'll see how we can, but first we present some simulation data. The simulation results are shown by the dotted lines. To get the current I1 minus I2, we add another circuit element onto our differential amplifier called the current mirror. The side where the common gate is tied to the drain, left side in this case, has some current, I1 flowing through it. The current mirror induces the same current on the other side. Some amount flows through the output node, and the rest, I2, flows into the differential amplifier. The amount that flows out is I1 minus I2. This configuration is called a transconductance amplifier. Here again we have some measured data, but it is not symmetric like we would expect. When a differential input of 0 is applied, some current still flows to the right side. This can be due possibly to transistor geometry mismatching the current mirror. In the last part of the experiment, we extract the gain and related parameters of the transconductance amplifier. Here we had the measured data of output voltage versus input, and we zoomed in on the high gain region. As before, the gain can be approximated as the slope of this region, to which we find has a gain of 282. Another parameter that can be observed is the output resistance RO, which has a value that's equal to the inverse of the slope of the output current versus output voltage curve. Lastly is the transconductance GM. We can do a check on our extracted gain value by remembering that gain is equal to the transconductance times the reciprocal of the output resistance, which has a value of 311 here. The discrepancy between this value and the previous is likely due to propagation error from the curve fits. We end by showing simulation results compared to the measured value, but unfortunately we could not very easily replicate the measured values.